YouTube engineer builds gravity-powered trebuchet that breaks the sound barrier. Add to Google preferred sources. UK aerospace engineer and YouTuber Tom Stanton has built a gravity-powered trebuchet that launched a 4-gram projectile at 776 miles per hour, breaking the sound barrier. By using a 3:1 pulley system, a carbon fiber arm, and a precise mechanical release mechanism, Stanton overcame the natural speed limits of traditional trebuchets. After structural failures at 50 kilograms, he achieved supersonic flight with a 40 kilograms counterweight and a lighter projectile, producing an audible sonic boom. Key elements: YouTube engineer builds gravity-powered trebuchet that breaks the sound barrier. A British aerospace engineer has accomplished what medieval siege masters never could, building a gravity-powered trebuchet capable of launching a projectile faster than the speed of sound. Tom Stanton, a UK-based creator with over 1.5 million YouTube subscribers, documented the build and its dramatic success in a recent video, culminating in an audible sonic boom from a device that relies on nothing more than a falling counterweight. Stanton's 4-gram projectile reached 776 miles per hour, or 1,249 kilometers per hour, edging past the sound barrier by roughly 9 miles per hour. The achievement was confirmed not just by the telemetry on his screen but by the sharp crack echoing across the test field, a sound never before produced by this class of ancient artillery. A conventional trebuchet uses a heavy counterweight dropping under Earth's gravity to swing a long arm and hurl a stone from a sling. Because gravity accelerates all objects at the same 9.81 meters per second squared, simply piling on more weight does not increase projectile speed beyond a natural limit. Stanton had to fundamentally re-engineer the machine. He suspended the counterweight from a 3:1 ratio pulley system, altering the mechanical relationship between the falling mass and the arm's rotation. The arm itself had to be exceptionally rigid yet lightweight, so Stanton machined it from carbon fiber using a CNC mill he had previously built at home. Early stress tests revealed weak points that forced him back to the drawing board for several redesigns. Another critical modification involved the release mechanism. In a traditional trebuchet, the sling releases the projectile at a fixed point in the arm's arc. Stanton's design wound the projectile rope around a drum attached to the arm, forcing an additional rotation to build velocity. That extra rotation, however, narrowed the release window to approximately 0.0025 seconds. His solution was elegantly low-tech. A mechanical latch inside the drum triggered the moment enough rope unwound from the dropping weight. Testing proceeded in stages, with Stanton adding counterweight in 22-pound, or 10 kilogram, increments. A 10 kilogram weight launched the projectile at roughly 394 miles per hour. At 40 kilograms, the speed climbed to 716 miles per hour, just 51 miles per hour short of the sound barrier. When he attempted to push the counterweight to 50 kilograms, components of the trebuchet failed under the stress. Forced to work within the machine's structural limits, Stanton returned to the 40 kilogram counterweight and reduced the projectile mass to a scant 4 grams. That final adjustment proved decisive. The arm spun up to 2,342 revolutions per minute, and the projectile exited the sling at 346.4 meters per second. The speed of sound at sea level is roughly 767 miles per hour, or 1,235 kilometers per hour, and Stanton's lightweight projectile cleared it with room to spare. While the era of trebuchets as weapons of war ended centuries ago, the project highlights how modern materials and precision manufacturing can unlock performance that medieval engineers could only dream of. Stanton's channel has previously featured an air-powered airplane, a bicycle driven by a Stirling engine, and a pendulum-powered mechanical system, each blending historical concepts with contemporary engineering. The supersonic Trebuchet stands as both a physics demonstration and a testament to iterative design. Each failed component and shattered part fed directly into a stronger, more efficient machine, proving that even a 1,000-year-old concept still has room to surprise.